So,
Ibrahim bhai,
yeah,
we are waiting for the participants. Or
okay.
okay.
Very good morning,
Good
Karthik
morning,
sir.
Professor David. Hello, hello. Yeah,
Hello, sir.
good morning. Good morning, Professor Dr. Sheikh. Yeah.
Good morning, one and all. Am I audible? Ibrahim sir?
Yes, you are.
Yes.
Yes, yes, you are
Thank you.
available.
Thank you. Assalamu alaikum wa rahmatullahi wa barakatuh. Good morning to one and all.
Alaikum assalam wa rahmatullah.
We welcome all the participants, our guest speaker today, and all the staff members, all students here. And I request Professor Shahab David to please have some verses of Holy Quran to start with the session. Professor Shahab David.
Thank you, madam. أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. قل للذين كفروا إن ينتهوا يغفر لهم ما قد سلف وإن يعودوا فقد مضت سنة الأولين وقاتلوهم حتى لا تكون فتنة ويكون الدين كله لله فإن انتهوا فإن الله بما يعملون بصير وإن تولوا فاعلموا أن الله مولاكم نعم المولى ونعم النصير صدق الله العظيم.
Jazakallah, sir. Thank you so much. Now I request Dr. Zakir Ilai, sir, to give some opening remarks for the webinar. Zakir Ilai, sir.
Okay.
Yeah, please
now,
take on.
Thank you very much. Good morning to one and all. And it's my privilege to give the opening remark on this today's seminar, battery technology. In fact, in today's world, machines and plethora of electronic devices surround the humans. The growing market of the electronic and electrical devices and thrust to sustainable developments is a driving force for the development of batteries as energy storage media, which are extensively used to power small gadgets. We know that renewable energy like sun, wind, tides have huge potential in providing us electricity in an environmental friendly manner. However, its intermittency and non-dispatchability are major reasons preventing full-scale adoption of its generation. Energy storage will enable this adoption by enabling a constant and high-quality electricity supply from these systems. But which storage technology should be considered is one of the important issues. We know that vast consumption of fossil fuels and increased greenhouse gas emissions bring about drastic environmental impacts that have led to an increased global demand for developing methods of harvesting and storing energy sustainably. Renewable energy sources such as solar, hydro, and wind energy are the most promising solutions for addressing these concerns. However, electricity produced from these sources must be efficiently stored to supply the world with energy on demand. Among the various energy storage devices, secondary batteries currently used in consumer electronics represent the leading electrochemical energy storage technology due to their high energy density and their accessible range of chemical potentials. Nowadays, great efforts have been focused on various kinds of batteries to store energy: lithium-related batteries, sodium-related batteries, zinc-related batteries, aluminum-related batteries, and so on. In addition, the construction of these batteries can be changed into flexible, flow, or solid-state types. There are many challenges in electrode materials, electrolytes, and construction of these batteries. Therefore, the research related to the battery systems for energy storage is extremely active. A roadmap which can bridge the gap between the academic research and commercial needs is necessary. Therefore, a continuous research on advanced cathode materials with high density and high loading, high efficient electrolytes, safe and stable anodes, functional separators, and high efficient binders is necessary. I am sure that today's webinar will give an input on the latest trends in the battery technology, which is the technology of today and tomorrow. At the end, I would conclude that the proper decision taken at the proper time, the right decision taken at the right time, is the need of the time. That's why, to say in few words, that एक पल के रुकने से दूर हो गई मंजिल, एक पल के रुकने से दूर हो गई मंजिल, सिर्फ हम नहीं चलते, रास्ते भी चलते हैं. If we do not decide, if we do not take the right decision at the right, we will not be moving along with the world. So this is the need of today. I appreciate the efforts put in by the NDLI Club and especially the organizers. And I am very thankful to the resource person of today, Mr. Karthik, that to have this beautiful and wonderful seminar today. Thank you very much.
Thank you, sir, Dr. Zakir Lai, sir. Now I request, first of all, I would like to introduce our speaker. He is Mr. Karthik, sir, and he is going to give us a webinar on battery technology. As sir has, I hope all the participants are now aware and got a brief description of the webinar from Dr. Zakir Lai, sir. So he's going to give you all the details about the battery technology today going on. And I request now Professor Fareen Bubere to give a keynote address. Yes, Professor Fareen Bubere, are you here?
Assalamu alaikum and good morning, everyone. Am I audible?
Yes, yes. Walaikum assalam. You are audible, ma'am. Please proceed.
So we all know batteries are making fast pace in markets and thereby revolutionizing the conventional system into the latest modern technology. Like we all are seeing that IC engines are very fast getting replaced by EVs. So as the world is advancing in the field, as well as we are advancing in the field of AI and ML, we cannot imagine the advancement without batteries. So batteries have wider application not only in the industries but also in medical as well as domestic areas. It has been an enabler for alternative propulsion and mobility solution, and thereby demand for advanced batteries is continuously growing, and that too exponentially. So hence creating requirement for sustainable supply of battery materials at a global scale. So now we can imagine that we require sustainable supply at a global scale, which is very critical. Therefore, we have our expert, Dr. Karthik Jamadar, who will explore the pathway to sustainability through new materials, development of battery, recycling, sustainable mining. So welcome everyone, and let's learn the advancement in battery technology through our expert. Thank you.
Thank you, Fareen, ma'am. Okay, so we'll continue with the further program. I request Professor Shahab David to give an introduction of our resource person. Shahab David.
Thank you, madam.
Yes, sir. Yes,
It's an honor for me to introduce such a person who is from industry background in and research. Okay, so Dr. Karthik Jamadar is has having 71 patents in the lithium-ion batteries, and he is working in Volkswagen, Germany. So he has completed his graduation from Mumbai University. Then he had completed his masters from IIT Bombay, and again he has did his second masters from Germany, and completed his PhD from the University of Stuttgart, Germany. So he has did the masters in Germany also. He is bachelor in production engineering, and he is specialized in battery technology and electric motors from Otto University in Wolfsburg in cooperation with the University of Aachen. He has many patents. As I told you, it is very difficult to introduce such a person who has many things. So I will just tell some point of that. Is it okay, sir? It is very. It is. You are such a nice person that I will just take the brief of that. So currently he is a supplier manager for lithium-ion battery cell pack in a purchase department at Volkswagen, Germany at Wolfsburg. His working areas are responsible for the cost, quality, and delivery schedule for the lithium-ion battery. He is a technical supporter for the purchase department of lithium-ion battery cell and pack. Earlier, he used to have a process planner in tooling division at Volkswagen, Germany. And before that, he has a product read lines manager for Volkswagen, Germany. And during 2018 to 2021, he has a battery planner and technology developer for battery manufacturing at Volkswagen, Germany. And working areas from other earlier departments, he has a feasibility analysis of single parts and assembly using simulation tools from ESI and Autoform. worked as a project manager for development of Bentley Continental, and he has commercial worked as a product readiness manager for Crafter. He has developed he has involved in the development of new technologies in the area of material utilization, process optimization, lightweight body, and cost efficient tooling. He has trained more than 500 people in the areas of lithium ion batteries, e-motors, and battery technology. He has did many technology projects related to the lithium ion batteries and the development of new concept for the high speed stacking of electrode and separator of lithium ion cell, development of new pressure welding for current collector welding in ion lithium ion cell, and he has did in manufacturing processes also in the competence area, metal forming, welding, joining, machining, and casting processes, tooling development, and lithium ion cell and module manufacturing. Uh, he regularly used to go to series of lectures at IIT Bombay as a honorary professor in the following areas: basic of finite element method and continuum mechanics, design for manufacturing, lightweight technologies, e-mobility, that is battery technology, battery manufacturing, hybrid drive, and e-motors. And recently in the past month, that is December, he was in IIT Bombay for battery technology, and in the last month, that is in January, he was in HVNIT for battery technology schedule Gyan program, and he has 15 number of publications also. So I will out of 71 patents which he has, I will just name a few of that. He has but all the patents are in mostly in the German language. So I will just read one of them. So positioning and trimming of separators and anode with respect to cathode for continuous high speed stacking direct from 4 coils. So without any pre-cutting of separators for the production of lithium ion batteries. Okay. So he has many such patents. Okay. So with this, I request such a Dr. Karthik Jamadar to take further. Thank you, sir. Thank you very much.
Thank you, Professor Dabir. It was my pleasure. And thanks, Miss. Can you hear me very well?
Yes, sir. Yes, sir.
I hear some noise, that's why.
Echo
Okay,
sound is
fine.
there.
Yeah. Okay,
You
fine.
are-
Now it's okay.
Now fine.
So, thank you for the introduction. And yeah. So today, I'm really honored to be there here with you all. And basically, I want to discuss with you the lithium ion technology on in next 1 hour, where we will explore where the roadmap is going. So basically, everything is introduced about me, so I don't want to introduce myself in that direction again. I just wanted to say that, as Professor Elahi also said, that we have been looking at the battery technology nowadays very seriously because of the global warming. I just feel one word, and I've been seeing a lot of places that India has seen a lot of revolutions, right? From the say automation in the farming division to IT divisions to digitalization. The next revolution which India will see is the lithium revolution. We have to go into the area of lithium
Sir,
technology.
1 second. The
Yes.
the speaker is making one sound that I
Okay.
don't know from where it is coming.
Okay.
Your speaker is making a sound,
My
back
speaker is
sound.
making sound.
Mic or
Okay.
speaker what?
Okay. Is it okay now? I put it more closer now. Maybe I will present it and close the video. So in that case, that will be better. Okay. So I'll start with my. Is it okay now?
Yes, sir.
Okay.
When you may turn on your mic, we will come to know.
Yeah, mic is over. Okay, now mic is there. Mic is working. Uh, or maybe I can directly use
Yes,
the.
please carry on. Please
I
carry
can
on. You are
directly use
audible.
the. I can directly use my computer audio. That also is possible without using the mic.
Now, okay, sir. Okay,
Please
okay. It's
carry on.
Okay,
okay.
Please
Voice
okay,
is
carry
okay.
on. You are
fine. That's
clearly
good.
audible.
Thank you very much. So let's start with the presentation, and uh, so can you see now some presentation coming up?
Not visible, sir, yet.
No, no, not visible.
Okay, so I have to do something more here. Hmm, because okay. So eine Fenster, ganze Bildschirm teilen. And now, is it okay?
Yes, sir. Now visible.
Okay,
Yes, yes.
that's great. So, so basically, in this lecture, no doubt we will be going on the more basic information. But believe me, it is more important to learn the basics first than understanding the more complex thing. So, basically, when we're talking about lithium-ion technology, or maybe I would say the overall the battery technology, it is not a new technology. In fact, it has been known for much, much before the IC engine which arrived. In 1719, uh, 1790, the Galvani, who was actually that time the biologist, discovered accidentally the electrochemistry. And he was actually doing experiment how to analyze the, say, how the electricity really works on our muscles. And accidentally found that even without any giving extra electricity, when he was connecting the two, I just show the video here. So basically, he was basically, so what happened that, 1 minute, why it is not happening? So basically what happens that, that he was basically using the two different electrodes or pins, and he realized that after that the frog which was actually dead, his his leg was dancing, and that was one of the reasons that we could say that, somewhere the current was actually playing a big role in basically the muscle movement. But what he accidentally realized it, that where this current is coming up, that current was coming mainly from the basically two different electrodes, and that was the reason that he found out that the two different materials basically can give us the voltage, and that is basically the starting of our electrochemistry. And that's how the word electrochemistry also came from the word galvani or galvanization. So based on the galvani experiment, many people then started realizing, okay, what could be the possibility of using this technology or this knowledge. And they found out that every electrode or material has different kind of voltages, and this was given here, that the lithium has the highest negative voltage, and there are some other material like gold, platinum, and palladium has the highest positive voltages. And they decided that our zero voltage is hydrogen, so hydrogen was taken as a basis. So it was very much earlier known that lithium has the highest negative voltage of minus 3.05, and we basically has other metals like gold, another thing which has a positive voltage. Now when we want to make a battery, basically we want basically one negative voltage and one positive voltage. Normally in our manufacturing process, galvanic process, we always called anode as a basically positive and cathode as a negative. In the battery we exactly says opposite one. We say that the anode is negative because it is a discharge state of battery, and the cathode is positive. And if you want to make a better, bigger and better battery, basically we want basically high voltage between anode and cathode. So obviously people will say, okay, the best anode material would be the lithium, which is having a minus 3.05. Lithium has some additional advantages. It is basically coming number 3 in the periodic table. It means it has very light material. Luckily it is available in the solid state, so we can easily make the paste of it and we can use it very effectively. It has a basically melting point of around 180 degrees centigrade, so basically it is not having problem like that of sodium. And at the same time, lithium also being a very lightweight material has a good affinity of giving a high energy. The lithium has the highest capacity in terms of energy. Normally, we call it that one lithium kilogram can give you around 12 kilowatt hour, so much of energy. No material can give so much of energy. So lithium had a good potential. So luckily, we found a very good anode material and we want to stick to it. That is lithium. The main problem started happening on the positive side of it. Which material we should take it? Because all positive materials which were available, I'll just show it here. Uh, they were basically of very expensive, or maybe I would say a more noble material like gold, palladium, those things, and giving maximum around 1.5 volt. And then basically they realized that why not use basically the non-metals. The non-metals have a very good characteristics, and if you see the fluorite has equally that high positive voltage of 3.06. It means if I would be having basically a battery between lithium and fluoride, I would get around 6.11, 3.05 coming from lithium and 3.06 coming from the fluoride. 6.11 volt, very high voltage. But unfortunately, fluoride and the lithium reacts say explosively, and it is difficult to break them again. When you want to make a basically a primary battery, that is one way battery, it is not a problem. One can maybe use it. But when you want to use a secondary battery, we want that lithium again come back to its original position. And at that time, the fluoride will not release that lithium. You will have to give so much of high energy to release that lithium from the fluoride. So that fluoride was out. Then the chloride, which was giving 1.36, was also out because of the toxicities. And at the same time, very high affinity to the lithium. And then came the word oxygen and water. So basically, we know that the hydrogen is zero. The who is giving that basically the potential for the water, I would say, was giving basically oxygen part of it, 1.23. And that is basically our starting point of the cathode. They started realizing that the oxygen could be a very good cathode material. And that's how started the first battery with the lithium oxygen batteries. But lithium oxygen batteries were like more like a open batteries where oxygen was coming. And what was happening that lithium and oxygen were making basically two different kinds of compound. One is lithium peroxide and one is lithium dioxide. One was irreversible and one was always reversible. It means every time there was a discharge and charge, we used to lose the capacity. So basically, reacting of lithium with oxygen was not a good idea. And then came the solution. Why not have a something like a metal oxide which is holding oxygen? And basically, the lithium is occupying the space between metal oxide, and the metal oxide is such a way that you have a transition metals, and these metals take up a different oxidation state and can occupy this incoming lithium. At the same time, when lithium wants to go away, this metal oxide can take a different oxidation number and release the lithium. So you can see here, basically when you are discharging, what is happening? This metal oxide is releasing lithium. It is coming into a different oxidation number. At the same time, when you are charging it, basically the same metal oxide is producing a different compound with making a different oxidation number. So we need a metals which could basically change their oxidation number in charge and discharge condition. And if we could have it, then basically lithium would just occupy the spaces between the metal oxide, make a covalent bond, not a very strong ionic bond. It means the lithium can easily come out of that metal oxide matrix and move towards the lithium metal as an anode and come back again. I will not go into the detail at present. What is that metal oxide? So then we found a good battery, one obviously with a negative lithium as an anode, nothing better than that. That was a lithium metal foil. And on the positive side, we have these metals, which is a transition metals, changing the oxidation number, having the oxygen. The oxygen was creating the primary voltage, but the metal oxide was allowing the intercalation of the lithium, and the lithium was basically occupying the space. So this was happening during the basically discharge state. Same thing was happening during the charge state. When I was giving external current, the lithium from the metal oxide would basically move because of the difference in voltage from metal oxide to the basically the lithium metal. And that's why you can say that lithium was basically untouched. It was like a rocking chair mechanism. Like, your chair is rocking. Similarly, the lithium is moving from anode to cathode and cathode to anode without actually your electrolyte taking part in the reaction. Obviously, there is an electrolyte in between. So basically, lithium ion cannot move without that. So electrolyte was allowing the lithium ion to move. But very important difference between lithium ion technology and other battery technology is that electrolyte is just there for the ionic movement. It is not taking part in the reaction. If you see normally the zinc copper batteries, or if you see basically the batteries which is our typical lead acid battery, you see that the basically electrolyte takes a part in that. Electrolyte get converts into it, and the ions which are moving are not basically the ions of lead or something. It is a sulfate ion, or if you have zinc copper, you also have sulfate ions which are moving. Here the lithium ion is moving through the electrolyte. And what was the reason, what is the advantage of it? That you have very very high efficiency in lithium ion technology. We are talking about 97 to 98% efficiency of this material. So you can imagine that I'm giving 100% basically energy, I'm getting a at 98%. Nothing is that better efficient than that, and that can continue to around 4000 to 5000 cycles. Your capacity loss is very very low. So it is a wonderful battery. Plus we know that lithium has a very high voltage, and the copper, this metal oxide, has around voltage of 1.23. So we are at least getting more than 4 voltage. So 4, between 4 to 5, normally we tell it around 4.2 to 4.3 volt. This is at least 4 times more than the conventional voltage which we know with the lead acid battery. Now we talked about voltage, and very important part for the energy is two: voltage and the capacity. What is capacity? Capacity is ampere hour, how much current is flowing in the hour. Now, basically, what is happening every time the lithium is moving from anode to cathode, it releases one electron, and that is what we call it as a current. So, basically, when we are talking about the capacity, we want to have more and more amount of lithium ion inside the body. Now, here we have a basically abundance amount of lithium because we are using a lithium metal as an anode source. So, there is no shortage of lithium. There is lot of lithium is available. So, basically, this battery can give you very high ampere hour because there is lot of ions are available inside it. Plus the voltage is decided by the two metals, which is fixed. So voltage cannot be changed. Voltage is decided by the material, and the capacity is decided by the mass of the lithium ion. And since I've got a good amount of lithium ion, I've got good abundance of lithium ion. Now this battery would theoretically be giving me maximum around, I would say, 10 to 11 kilowatt hour per kilogram. That is extremely high energy. Unfortunately, this battery does not exist. Why? The reason being that when actually lithium was coming every time during the cycle and getting deposited on the lithium metal, they were not getting deposited uniformly on the lithium metal. They were basically forming the dendrites. So it would imagine that there were some peaks and valleys, and that peaks would keep on increasing. And we know there is a separator in between. And the separator is such a way that the basically the ions can move through separators, but electrons cannot move through separator. Now, if the dendrites would keep on increasing, then these dendrites would eventually penetrate the separator and will touch the cathode. And then we are giving a short circuit. It means the electrons are moving not outside the battery, they are moving inside the battery. And that means there will be heat generation. And eventually, because the electrolyte is basically a flammable material, there will be explosion. So these batteries were not safe. And because of that, the lithium metal batteries for long time had no future. People thought that no, it is a very good thing. It is very unsafe batteries. So you can see this is like a dendrite structure which is produced mainly on the anode side because of the non-uniform deposition of lithium, and these dendrites would eventually make a short circuit. And people tried many different ways to change into the electrolyte. One way of research went into the polymer electrolyte. They found that polymer electrolyte is somewhat better against the dendrite. The one research went into the solid state batteries, saying that we should have something like a non-flammable uh, solid electrolyte, which we call it as a ceramic based electrolyte. So this all started in the 1800. You can imagine it is not a new technology, but still no surety was available. And then came a new idea from Sony in 1990. So you can imagine 200 years we lost in that. And he and the that idea also came very accidentally. That person was basically doing a research on lithium ion technology, and he was finding that how can I remove this dendrite. And his daughter was next to it, and he says like this lithium metal is causing a problem for me. She very clearly said that remove that. He was extend how can I remove anode only? If I remove anode, there's nothing else. But then exactly that thing suggested, oh, if I can change the source of lithium from anode and put it into the cathode side, then what happens? I am interested to have lithium ions which are intercalating inside my cathode. I don't really need lithium metal, and lithium metal is causing this dendrite. And that's how the wonderful idea came with lithium ion technology. They removed the lithium metal completely and they put the graphite. The graphite replaced the anode. The graphite has a wonderful properties. It can intercalate lithium ions inside the say the layers of graphite, and it forms basically a stable compound called LiC6. It means every six carbon atom can hold one lithium ion with a covalent bonding. On the cathode side, nothing had changed. Same metal oxide was there, and metal oxide was basically holding the lithium. The only difference was that now the our source of lithium was cathode. It means when I'm making the battery, my lithium is not on the anode side, my lithium is there on the cathode side, and this cathode is basically having both metal oxide and lithium, and this lithium need to be transported from cathode to anode during the first charging process, and that is basically done by your manufacturer. So basically they are shifting this lithium from metal oxide to this, and now since there is no metal, the lithium is intercalating deep inside the graphite electrode. There are no chances of having the dendrite, and since there are no dendrite problems, we can say that the whole thing become very easy. The safety of the cell increased, but at the cost of the weight, because as I told you, you need six carbon atom to hold one lithium atom. It means if I need more and more lithium atom for more and more capacity, I need equivalently more and more carbon atoms. Now these carbon atom actually are not actually helping me in the energy. They are just helping me in the process of basically intercalating lithium inside my carbon. But if they are not helping me and still I need it because of the safety, no doubt my energy density is going to go down. So the energy density, which was basically, you can say 11 kilowatt hour per kilogram for the lithium metal batteries, theoretically possible, reduced to 300 watt hour per kilogram, 2%. So we were only getting 2% of the energy which theoretical lithium could give you. But only with this new idea, lithium ion cell technology was safer and feasible. So basically, this is basically how the lithium ion cell technology basically happened from lithium metal technology. Nowadays, we are thinking how to increase the energy density more and more by changing some kind of metal oxide, changing some kind of graphite, putting some other materials that we will see now, so that we can increase the energy density. But the principle remains same. Now we have many different kinds of lithium ion cell. People call it NMC, that is nickel manganese cobalt cell, or people call it LFP, lithium iron phosphate. People call it LTO, lithium titanium oxide. Now these are basically not a different kind of cell. They have the same technology. Only thing, your cathode material is different. So when we are talking about NMC cell, you must have heard of it, NMC, nickel manganese cobalt, which is practically used in automobile industry. So what they are doing it, they are, instead of using this metal oxide, which I just said metal oxide, they're using nickel, manganese, and cobalt in different proportion as a basically holder for oxygen. When we're talking of LFP cell, lithium iron phosphate, basically iron phosphate is basically the cathode material used to hold the oxygen. When we are talking about LTO, lithium titanium, here instead of graphite, we have a titanium oxide which is holding the lithium. So basically, the principle is same. Only thing we are changing anode or cathode. Now, someone can ask me how much energy density, what actually you can convert that energy density into the kilometer range of the car. You can imagine. And then you will realize why the lithium ion cell technology has no congruence. If you see the energy density, we have a lead battery would give around 100 kilometer. Suppose I want to travel 100 kilometer my car. Normally, the 100 kilometer with I would say normally I would give a Volkswagen. Just take a Volkswagen Polo. It would give you around 16. You need 16 kilowatt hour for energy. You know, either you give this energy by IC engine, by fossil fuel, or you give the energy from the battery. The amount of energy is same. Now that 16 kilowatt hour, if I need energy, I would need around 533 kilogram of lead batteries. Then came the secondary battery called nickel cadmium battery, which is more or less nowadays prohibited because of the toxicity of the cadmium. We needed 320 kilogram. So in the energy density side, it was better. When we went into nickel metal hydride batteries, we could realize that it needs only 220 kilogram of the batteries. Now came the next generation batteries, lithium ion technology. We need only 123 kilogram. It means one fourth of the battery. So normally we give a ratio that 1 kilometer needs 1.2 kilogram of battery weight. This is something, say, I would say 10 years back. Now the ratio has gone to 1 kilometer, 0.8 kilogram battery. So you can imagine that as we become more and more energy density, we are getting more and more kilometer for the same amount of mass. And that's why we can say that lithium ion cell technology has made e-mobility possible. Otherwise, it was unthinkable with so much amount of weight happening with this other kind of batteries. And now this here is a range of 120 watt hour per kilogram. If you have seen the Tesla cars, the latest one, they give 280 watt hour per kilogram. So we have already given more than the double of that energy. The the LGs and the CATL, the big manufacturer of the batteries, have already said that they would go up to 300 watt hour per kilogram in the next generation batteries with lithium ion technology. So you can imagine that if we reach those things, and which is very much possible in the next 2 or 3 years, we would get much more basically mileage for the same weight. And this is basically the most important thing, that the energy density of lithium ion is extremely high. Obviously, that also causes a risk factor in it, because if you have very high energy in the same mass, and if that get released, it can cause to explosion. But believe me, lithium ion cell technology, if it is handled properly, it is equally safer or even more safer than your IC engines. Now, this is a very important diagram, which we call it as a Ragon diagram. Normally, when you drive a car or when you drive a basically electric car, you don't just need the mileage, but sometimes you also need the power to give that acceleration, to go that boost function. Similarly, like if you are having a power tools or something, you also need that power. Now, earlier, what was there? If you need a power, they would always use this lead acid batteries. Lead acid battery had a very good power, and but at the same time very less energy. The nickel cadmium nickel metal hydride battery were giving a little bit more power and more energy. But now, if you see this part of it, lithium ion technology, it can give a very good energy density, energy also. At the same time, fast 10 times more power than the lead acid battery. It can work both the ways. It means if I want a high power, it means a high current in a short period of time, lithium ion can give you. If you need a high energy, that also can give you. Only thing, it cannot give both the things simultaneously. The principle is very similar, how we have the lithium ion technology, but either it can give high energy or it can give high power, but not at the both at the same time. The reason being, basically, I can explain here. The lithium ion has to move from graphite to basically the cathode. This is a distance which they have to move. Now we know that the ions move at particular speed, which is basically controlled by your electric field, and they have to travel so much of distance, and then only when basically ions reach here, they will release electrons. Now, if I need high power, basically I need high current in a short period of time. I need that the ions should move faster, or they should cover the same distance in short period of time, but I cannot increase the velocity of the ion. So what I have to do it, I have to decrease the distance between them. So for the high power batteries, what we do, we have this coating thickness, which is basically practically one fourth the size of the high energy density. So because of that, everything becomes very, very closer to each other. The ions have to travel very small distance, and that's why they can reach other electrode faster. And because of it, they can release electrons. Same way basically happens that, if we basically go from the charging to discharge, they also have to travel shorter distance. If you don't high energy, basically high energy, as I told you, you need more active materials. More active material means you need more masses. It means you need more coating thickness, and it means the high energy batteries will have more coating thickness. High power batteries will have small coating thickness. That is basically the small difference, or I would say only difference between the two batteries. The rest of the things are more or less very minute differences are there. I hope you can hear me. Huh? Just tell me because I'm keep on. Is
Yes,
okay?
sir, you
I'm
are
audible.
audible.
Okay,
Yes,
thank
Yes,
you.
sir. Yes, sir.
So
Yes, sir. You are audible.
okay, yeah, 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 yeah. So basically, as I told you, everything in life comes with some compromise, and that is here in lithium-ion cell technology also. You have a very high energy, but that high energy is available only safely in some particular window of voltage and temperature. If you exit that window, then you are in the very unsafe zone. So basically, normally we call lithium ion cell technology that it will work between 2 to 4 volt. I would normally sell it around 2.5 to 4 volt. If you exceed that 4 volt, it means if you want to charge your battery more than 4 volt, normally we can go maximum now with our electrode 4.3 volt. After that, what happens? Exactly, everything is connected in this graph. The metal oxide, which normally should hold the oxygen very strongly and only change the oxidation number so that it can hold lithium also, they do exactly reverse way. They release oxygen at 4.3 volt. And the nickel is one of the main culprit in that. The nickel releases oxygen very fast. Now, if you can imagine, your oxygen is released from the oxide. You have a flammable material like electrolyte. A small spark would lead to explosion, and that's basically happening more than 4.3 volt. So basically, you have to control the charge of the battery more than that voltage. You cannot charge it. Secondly, what happens when we discharge the battery, when we are using the battery and go less than 2.5 volt? The 2.5 volt, if you go with that, what happens? Normally, this metal oxide is basically pasted on aluminum foil, and this basically, sorry, and this graphite is pasted on the copper foil. Less than 2.5 volt, the lithium will move, but at the same time, copper from the copper foil will also move towards the graphite, towards cathode. So we have two ions coming, copper ions and at the same time lithium ions. The copper ions will again come back to the copper foil and make the dendrites, similar to the problem with the lithium metal. And then we will have some kind of dendrite short circuit. So basically, don't go less than 2.5 volt. Who is controlling that? You don't have to worry it. There is a battery management system, which we call in short BMS, and that is basically controlling the temperature range. If one battery has reached that temperature, immediately that battery will be discontinued or disconnected, and this can be done by passive BMS or by active BMS that are like and that way the battery will be controlled within that zone. It is very, very important that we have to respect this voltage zone. Now comes the temperature. In the temperature, what happens that if you are basically going above some particular temperature, and that comes in different from just from the first 60 degree onwards, what happens? I explain everything here with this diagram. So basically, what happens if you go immediately 60 degrees centigrade and more? Basically, the lithium ion technology, what happens that there is some kind of protective layer which is formed on the graphite, and that is formed by the electrolyte. So that it is only formed one time, and that we call it solid electrolyte interface. It is a very important protective layer. Otherwise, what happens that graphite will every cycle deteriorate. But once that protective layer is formed, it does not get deteriorated. Now, that protective layer is a very important phenomenon for the life cycle of the battery, and that start getting deteriorating around 60 to 70 degrees centigrade. So that is the first effect. You will see that the life cycle of the battery goes down. More than 80 degrees or 90 degrees, you will start realizing that your separator starts shrinking up. It means there is a chances of electrode contacting each other. If you go more than 90 degrees centigrade, one of the constituent of the electrolyte, which is the dimethylene carbonate, DMC, has a boiling point. It starts boiling up. It means the gases will evaporate. The gases will be generated inside the cell, the internal pressure will build up, and the cell will eventually blow up. So you can realize that right from 60 degree onwards, we have a problem, that the security of the safety of the cell will be affected and the life cycle of the cell will be affected. Same thing happens if you go on the lower cell temperature. Normally, we call it till minus 7 degrees centigrade, lithium ion cell works in a very good efficiency of around say 97%. But after that, like if you go lower temperature, your efficiency or maybe is irreversibly affected. Why? Like there is an electrolyte here, and this electrolyte has a very important constituent called ethylene carbonate. Normally, these electrolytes, which we know from other batteries, are water based. Here, we don't have a water based electrolyte. We have a basically non water based electrolyte, carbonate based electrolyte. So, ethylene carbonate is important. And ethylene carbonate has a basically eutectic point at minus 7 degrees centigrade. It means after minus 7 degrees centigrade, if you go lower than that, it will become solidified. Now, you can imagine if I have an electrolyte which is becoming solid, the ions will not move very easily. The resistance to the movement of ion will increase, and because of it, obviously, my efficiency will decrease drastically. By chance, if you will still work with that minus 10 degrees centigrade and try to give a very fast acceleration to your car, immediately I want to go to 100 km per hour. You are forcing ions to move very fast, but the ions are basically not able to intercalate that fast because your viscosity of the electrolyte is increased. So what would happen? There will be lithium plating will be formed on the anode and cathode. Lithium plating is basically lithium metal coating, and this is not permeable to the ions. It means that my ions will not enter that region of electrode, and that area is completely blocked from the movement of ions. My capacity is permanently lost. So basically, lithium plating is one of the reason what happens at low degree centigrade. So basically, this is the graph we should always say that we should work in the optimum temperature of say minus 7 to around 50 degrees centigrade. 60 degrees okay, not more than that, and the temperature of 2.5 to 4.2 volt. And this is basically controlled by your battery management system. In case you will exceed the temperature and it is uncontrollable exceeding, it means it is increasing 1 degree centigrade per minute in that rate faster and faster, then the battery management system will give you an indication or warning that please exit your car, because that is basically the starting of thermal runaway, and then basically the thermal runaway will basically happen. Don't worry, don't feel that this is all basically very dangerous. In fact, lithium ion cell technology, or I would say electric car, is much more safer than IC engine car. In IC engine also you have a flammable fluid, like fuel, like a petrol and diesel, and there is no kind of safety there like a battery management system. Here you have a safety from first safety from battery management system, and second there is a safety coming from a basically a very important rule which has started, that when the thermal runaway starts, the 5 minute till 5 minutes your car will not end up having explosion. So every car OEM has to assure that thing, and then only the batteries or the car is able to sold. So basically you can imagine that you have 5 minutes after the thermal runaway started to exit your car and do that. And normally, the amount of accidents which happens in the electric vehicle is quite less compared to the accidents happening in the IC engine car. So I know that there are some issues happening in India from the scooter and the two wheelers getting exploded. Maybe there is some kind of problem with BMS because India is doing a starting of this car development. But once it is fully developed and safety, then these things will be becoming lesser and lesser. So basically, as I told you, we have very important metals which are important lithium metal. One is lithium, obviously. Other one, people are talking about using sodium and magnesium batteries also. Why? Because we feel that lithium is going to become more and more scarce. The amount of lithium is not that much available which we want for the electric vehicle growth. In the next 50 years they will start in the scarcity of lithium. So the sodium and magnesium are coming as a big alternative. Sodium has a more or less very similar voltage like lithium, but you can imagine that here we have a basically weight of 7, and here we have weight of around 18 to 19. It means immediately you can see that your weight of your energy carrying particle is more. That's why the energy density will also be less. The magnesium is even the same case. So they are both in a very research phase. This is wonderful place where you can also institute can do a lot of research in the area of sodium and magnesium batteries as an alternative to lithium batteries. On the other side, on the anode side, we have a carbon basically in the form of graphite. The carbon, as I told you, has a problem that 6 carbon has 1 lithium. It could be very interesting if we could find some material where it can hold more lithium for same amount of less mass. And there it comes the silicon. Silicon can hold 22 lithium for 6 silicon atom. So you can imagine there is a drastic difference. It means same amount of silicon can hold 4 times more lithium than basically the carbon. So there are a lot of research going on how to replace the graphite anode into the silicon anode. But as you can imagine, if your anode is actually holding more and more lithium, they will also expand, and their expansion will be more like 300%. Your cell will expand by 300% more if you have silicon because it can hold so much of lithium compared to around 18 to 20% in the carbon. And now the main problem happens how to control that expansion. So basically, there are a lot of research going on how to give a compression pad, uniform compression pad, so that the cell does not get expand, say non-uniformly and so on. And that's why we are not putting 100% silicon. We are basically having around 10 to 50% silicon in our graphite. The rest is still the graphite. And basically, the titanium is one of the material which can basically used instead of the carbon. You know, titanium is basically a heavyweight material, so basically the weight will be higher, the energy density will be lower. But a very important thing is that these titanium batteries are very stable batteries, very safe batteries, and basically it has no aging, practically no aging. It can live for years and years. But only problem is it has only basically 2.2 volt. So it cannot give you 4.2 volt like carbon with basically lithium and those things. It can only give you 2.2 volt. So basically you have very high safety, but at the same time at the cost of low voltage and at the cost of low energy density. So this titanium is basically used in the areas of basically aeroplanes and space satellites where actually the safety and the stability of the battery is very important and the aging should be practically zero. So in those areas we are using this titanium as an anode. But for the EV vehicles, normally we would use either carbon or carbon in the form of graphite, or maybe replace also with some kind of silicon. What are the cathode side? On the cathode side, basically, I told you we have basically very important part oxygen. It would be wonderful to have only oxygen without this metal oxide, but the oxygen alone cannot help you because it basically form a irreversible compound called lithium oxide. Other could be also one of the research thing is going on is to use the sulfur as a basically cathode material. Sulfur gives you low voltage but a very high capacity. It's a very interesting material. But most of the research or most of the present technology is focused on basically the three things: nickel, cobalt, and manganese. And these are the basically the metal oxides which are basically going to be used in the future. And this is basically giving us more or less, I would say, 300 watt hour per kilogram. And as we know that the cobalt price are increasing to the heaven, so basically everyone is want to reduce the cobalt, and they want to increase the nickel and nickel. So basically what is happening, nickel is giving me the main energy. They want to increase the nickel, but as you increase the nickel content, you also decrease the safety of the cell. So basically it has to be compensated by either little bit of cobalt or little bit of manganese. And that's why we have more or less at present the standard technology called 811, 80% nickel, 10% cobalt, 10% manganese. Uh, Tesla is using without manganese. They are using basically much more say risker, say unsafe technology. In that sense, I would say they have 85% of nickel, 5% of cobalt or 10% of cobalt, and 5% of aluminum. And basically, there's no manganese, which can give a basically good stability at high temperature. But that's why they are going with the small cells, because small cell has anyway less energy inside the cell. So even if the one cell would have problem, the complete cell pack would not get problem. But it would be unwise to go with the same chemistry for the big dimension of the cell. Uh, there is other trend going on in the same direction. At least for the Indian market, I feel it's very important if we could use basically cobalt free, nickel free material, because it's basically the cost is very important. And there comes the basically iron phosphate LFP. Iron phosphate has the advantage that it is a very stable. It does not explode. It is very safe cell, but it has an energy density which is half of the that of NMC cell. So basically, you will have to say compromise on the energy density, and it can maximum give around 3.3 volt. So normally we can get around 4.2 volt for NMC cell, and for LFP we can get only up to 3.3 volt. So basically, there is always some kind of compromise, but still I believe that for the Indian market and for a lot of other places, LFP could be a very good alternative because of the raw material abundance which is available and the price which is quite interesting. So basically, this is basically about the different kinds of cells. They are all working on the same principle, which we call it lithium ion technology. NCA, nickel, cobalt, aluminium; LFP, lithium iron phosphate; LMO, lithium manganese oxide; NMC, nickel manganese cobalt; LCO, lithium cobalt oxide. Each having its own advantages and disadvantages. LCO will be very high cost because of the high cobalt content. NMC has a basically the good properties in terms of energy density, but because of the high nickel content, it is a little bit unsafe. NCA would be highest energy density but more unsafe. LFP has a basically lowest energy density among all, at the same time very safe. LMO has a very high voltage, but at the same time it has a problem that it does not have that much high cycle efficiency. So one has to use based on it, which is the best one of for us. They are all available in the market. And this is basically a discharge curve which you see with the time. Only when we are talking about the LFP material, we should see that the LFP material has a very flat curve. It means it starts around 3.3, 3.4 volt, and immediately till the end, it is always having the same flat curve. And by somewhere before the capacity is fully gone, it goes down. That makes it difficult to analyze the exact how much amount the capacity has been used by this cell, because by every capacity the voltage will remain same. In other cell you can see there is a slanting curve. It means our BMS system can easily say, okay, you are at this particular region or this particular region or this particular region, and it can say whether my voltage is what should my voltage accordingly. LFP, finding the basically capacity is a difficult part of it. And as a result we can say that LFP has basically some problem with the BMS system. Otherwise, it is one of the wonderful cell, obviously with less potential. So basically, where are we going in the next trend? At present, everyone is talking about energy density, and that is the most important thing in the lithium ion technology. Now people are getting hungry of more and more energy. Safety has become a secondary issue. Initially, till 2015, we were working with basically 180 watt hour per kilogram, where we were using mainly 33% nickel, 33% cobalt, 33% manganese. It was quite good cell, getting compromise from all the three metal oxide. Nickel was giving high capacity, cobalt was giving me high voltage efficiency. It means even at around 4.3 volt, nickel would not release oxygen. Cobalt was suppressing nickel to release oxygen. And manganese was giving high thermal property. It means even till high temperature, nickel was not releasing oxygen. Then the cobalt price started coming up. The cobalt was only coming from the Congo region in the Africa, and there basically the big problem is also of the child labor. So the whole image shifted. The UNICEF started creating the advertisement that there is a lot of child labor going on in the Congo region. Please stop cobalt mining. So people realized, okay, because of the price and because of this child labor, we have to stop the cobalt. So they decreased the cobalt content. And nowadays, more or less, we are talking about 811, 80% nickel, 10% cobalt, and 10% manganese. The tendency is to go towards 9, 0.5, 0.5, that is 90% nickel, 0.5% cobalt, and 0.5% manganese. So obviously, we would see that we would have to sacrifice some kind of safety in that. But at the same time, your BMS system should be very sharp enough to get that voltage peak and should react immediately. Like you can say that, I normally give in my lecture example of, like, you have a class student where your hooligan child is like a nickel, and you have basically the students who are basically calm and who want to basically put this hooligan kind child into control, that is manganese, and there is a teacher who is like cobalt. And now what we have done, we have removed the teacher from the class, or we want to remove them. We want to remove the, say, basically silent and studious student from the class, and the class is full of hooligans. So what will happen is the same thing. No doubt it will have wonderful energy density, but we would have some problem also in terms of safety. So in that case, what we have to do, we have to increase the safety of the cell by putting extra mechanism. It means we have to see to it that we have to put the flame retardant materials like mica. We have to have a good separators with the ceramic coatings, so that there cannot be any short circuit happening in those things. So basically, yes, you can use high nickel content, but at the same time, we have to see to it that the safety of the cell increases. And that is also one stage I would say India has a big potential to improve, is because in every future module we will be using mica sheet to give the flame retardance. It means even if there is a flame happening in one cell, it should not get transported to other cell. And the mica is coming in the big way. More than, I would say, 5 kilogram of mica will be used in one module. And the India is one of the biggest producer of mica sheet. Okay, then I would say like till around 280, or I would say 300, we would reach our limit of energy density. More than that, it is not possible with the conventional lithium ion technology. If you want to go beyond it, there are three ways. The three ways is, one is lithium oxygen battery. Again, go back to that and try to see that oxygen basically react with lithium and does not produce lithium dioxide, only produce lithium peroxide. So for that, you need some kind of catalyst for that. Lithium sulfur could be interesting technology coming up. And the new system, mainly the solid state batteries. The solid state batteries had advantages that the cell is basically very say thin. Your separator is not there because your electrolyte is basically a solid medium, so it acts both as electrolyte as well as separator. So we are removing the separator part of that. And here, because there is a electrolyte which is basically in the form of ceramic, it also prevents the dendrite to migrate from anode to cathode. It means basically even now we can start using lithium metal as an anode, and we don't need graphite or silicon. So the solid state battery has a lot of potential. Here we can expect at least 20% rise in energy density, and energy density per weight, energy density per volume. And I think so around 550 to 600 we should come to the level where it is feasible by 2035, 2040. If that amount of level of energy density is reached, believe me, we would have more applications of lithium ion cell technology. Maybe the aviation would also have the battery technology. At present, we need minimum of 400 watt hour per kilogram energy density to fly planes with the batteries. With 550 watt hour per kilogram, you will see the planes are getting converted also into the green energy, that is the battery energy. So you will see drastic changes happening when we reach that kind of energy density. And then obviously the question reached, are we still finished, or maybe our human creative mind will always tell us more and more ideas. So this is about the solid state batteries, where actually earlier we have this anode, we have this cathode with the fluid electrolyte and the separator. Now the main problem happening in the battery is because of the fluid electrolyte. So you remove the fluid electrolyte and put basically the solid electrolyte, and you have to see to it that the solid electrolyte is basically mixed in thoroughly in such a way that every active material of graphite, sorry, active material of basically your cathode and anode have mixed with the solid electrolyte. That is the biggest challenge. Then you don't need a separator. And once basically it is realized, then we can say that we remove the graphite part of it, put the lithium metal, and then it will be also working. It means a very high energy density because now your lithium is there in anode side. It means you have lot amount of lithium. Lithium is in abundance. It means a lot of capacity is available. So now what we said in 17, 19, 1800, it was not possible to use lithium metal. In 2040, maybe we would, or maybe I would say before that, 2030, we would again go back into the past and say now lithium metal is possible, but with a different kind of electrolyte. So this is wonderful area of research of solid state batteries. All OEMs and lot of battery suppliers are having different strategies to make solid electrolyte batteries. If it would be so simple, obviously this battery would have come. The main problem is how to have a uniform mixing of solid electrolyte inside your cathode and anode, and at the same time how to prevent the cracks happening in this ceramic electrodes. So these are basically the two problems, which is one of the which is restricting the full usage of the solid electrolyte batteries. Sorry. So basically, I would just go fast on the overall part of it. Lithium cost structures. Everyone is talking about the cost of the battery, and when say cost of the electric car, you can say the 50% of the cost of electric car is the battery cost. So basically, where is this main cost coming? The main cost, normally, if you see, this is a battery pack with a number of cells which are supposed, we normally buy from the battery supplier. We also manufacture, no, we get it around $145 per kilowatt hour. If we would look at the individual cells, this is a typical LG cell, a pouch cell, it would cost around 84 to $85 per kilowatt hour. And there you can see the biggest cost is coming in the form of material. And now let's see the material part of it. The biggest cost is coming in terms of the cathode material, your nickel, manganese, and cobalt oxide. So that is basically the 43% of the cost. The rest part is separator, though it is just a polypropylene 3 layer sheets, but still because of the uniform porosities and the coating of ceramics, it is one of the very expensive material. And then the electrolyte anode and the other thing. So the main thing is if you can decrease the cost of the cathode material, you will automatically decrease the cost of the batteries and the cost of basically battery pack. Nowadays already it is published in a lot of newspaper that most of the OEMs are buying less than $100 per kilowatt hour for the battery pack. So you can imagine that the battery costs are decreasing every year, though the raw material prices are increasing every year. So basically there is a lot of potential to decrease the battery cost by improving the manufacturing automation processes, though we have to compensate in terms of raw material cost. So basically, up till now we have talked about the electrodes. This is about electrodes are forming the cell. The cell, there are a lot of electrodes like cathode, separator, anode, separator, cathode are stacked together. Then they form basically module. Uh, Sorry, this cell could be either in the pouch cell or in the prismatic cell. The pouch cell was normally started by LGs, and prismatic cell was basically the Samsung and CATL. Nowadays, people are going for the more prismatic cell idea. The Tesla is only one company using the round cell that goes in making module. One module is around say 7 kilowatt hour, and then finally the different modules are put together in series to get the final voltage. And you can see that the price is decreasing from 145 euro per kilowatt hour, which was just 2 years back, now to 90 euro per kilowatt hour. And there are different things important in the module battery pack. There's a housing with the battery modules. This is basically your cell management system. Basically here is a cooling plates. Basically the cooling plate will control the cooling of the battery, at the same time also the heating of the battery. And then you have basically the here on the top there is a battery management system which is placed. This battery management system will consult with the cell management system, will get the voltage of each and every cell and control the temperature and the voltage of cell. So basically that's how basically it is made up of. And obviously you have high voltage connectors, and this is basically connected to the finally the traction motors, which will get the voltage and the current from your battery. So basically as I already told, the main part of the material is basically the material part of it, the cost of the material part of it, and from that the NMC is playing a very important role. The other is quite manageable, and that is also increasing drastically, because if you can see the basically the growth of this EV vehicle is such a drastic there, that we can expect that is more or less like exponential curve, where both lithium, cobalt, and nickel and manganese, they will be used drastically more and more. And we have the big problem, there is not enough raw material available. Cobalt is coming mainly from the Congo. They have 3.4 tons, million tons of reserves, but our production is at 363,000. They expect that in next 10 years, the cobalt mines will be empty. The copper mines will be empty by 50 years, and the lithium would not be available more than 30 years. So we have to find some alternatives, and that the alternative is recycling process. So basically, we have to go for the recycling of the batteries, where we can use the same batteries and the same raw material again and again. For the battery side of it, it is no problem. One can recycle the material and use it again without having danger of losing the capacity. Only thing is, at present, the recycling process are basically done in the two ways. Either is pyrometallurgy or hydrometallurgy. Basically, you convert the battery raw materials into the black powder and treat it with the temperature pyrometallurgy, and vaporize each and every raw material and then condense it. It's a very energy intensive process. Another is a hydrometallurgy process, where basically different solvents are used to basically get different kind of raw materials. And these are the two different processes followed by many industries. And one can also get lithium, one can get cobalt, one can get nickel. At present, lithium is not used too much from a recycling process, because the cost of the recycled lithium is at present around say 3 to 4 times more than the primary lithium. So people are not using that lithium. But eventually, once the lithium price increases drastically, which is going to happen, then obviously the recycling of the lithium will also become very very interesting. So basically, you can see that these are the prices which are there. Cobalt, now just lithium, this was 43 US dollar per kilogram. If you can just see yesterday's or today's London Stock of Exchange, you will see that it has gone more than 60. So you can see that it is basically exponentially increasing lithium prices. Lithium is like nowadays people are calling it as a white gold, because it is basically available only in the few countries like Chile, Bolivia, Argentina, that is in the South America, and Australia is one of the supplier of that. I'm sure that India would also start with the mining of lithium or extraction of lithium, because if without lithium, and technology is impossible. And yeah, we have to extract lithium and see to it that we get also lithium. I'm sure that there must be some extracts also available in India also. And the other price which is increasing highly is the cobalt price of it. But cobalt can be still substituted. We have decreased the cobalt from 33% to now more or less 0.5%. So that effect is less, but lithium cannot be substituted. So this is one of the basically important graph. And basically, my last graph would be what is the next trend happening in the near future. Whenever everyone talks about e-mobility, people talk about the recharging time, how fast I can charge it. And that is basically also the constraint in people buying electric vehicle. Believe me, in the next generation of electric batteries which you're seeing, is a high speed charging possible. And high speed charging is possible because of the cell technology, where you have high silicon content, and you could theoretically go up to 4 minutes 100 kilometers charging. So it will be very very fast charging. Obviously, for that you need high watt power station for that. So those things also has to be developed. A lot of new business model will start coming up in the direction, but the charging time would decrease by 70% by 2025. Then production cost will reduce by 60%. Already we have seen from $145 per kilowatt hour to $90 per kilowatt hour. The tendency is to go down and down, though the raw material price is increasing. And the energy density, we would see that it increases by 300%. That is more or less coming mainly from solid state batteries. So solid state batteries would start replacing the fluid batteries in the near future. So this is basically the next trend which I'm exactly locating it, mainly in energy density, in the production cost, and rechargeable time. And all three are going in the positive way. Once it goes, I believe that the electric vehicle growth in worldwide, especially also in India, cannot be stopped. And basically, it is a good thing for the environment also. With that, I will s- close this presentation. I hope it was interesting for you all. And if you have any questions, please be free to raise that. Thank you.
Yes, sir. Students, faculty members, dear faculty members, any questions? Okay, okay, fine. Thank you, sir, for feeding us with full of battery knowledge. Indeed, your profile with 71 patents and 15 publication motivated us. And I'm feeling very proud to know that you are a Mumbai University and IIT alumni. Great, sir. Now I request Professor Atya ma'am to conclude our program with word of thanks.
I would just add one thing. I believe that mechanical engineering and manufacturing engineering, especially, would play a very, very important role in the future development of lithium ion technology. Because now everything turns into how we can efficiently manufacture the battery, how we can make that battery more energy dense. So people normally have the idea that battery is more like a chemistry or electronics. Believe me, it is 90% mechanical engineering. And that's why mechanical engineers try to use your ideas. Don't think that any idea is basically foolish idea, because believe me that how that Sony developed, if someone would have told at the time that we have to remove that lithium from the anode, people would laugh at it. But today, only because of that, we have lithium ion technology. So don't feel that any idea is wrong. We have a lot of new technologies which is established in other products. Try to see that those technologies can be used also for the batteries. And now the world has just risen up from this deep sleep. So everyone is looking at these ideas and creativity to make the batteries more efficient. And I feel as an Indian people, Indian students, you are really creative people. Think about those things and try to generate new ideas. Please. Yes, it's a nice question. Basically, I believe that before that EV can come, there is going to be a say bridge technology, and that is going to be the hybrid technology. So hybrid technology in terms of micro and mild hybrid is already available in India. Even the full hybrid has started coming up. The next trend which will come in India market will be plug-in hybrid, where actually you have both the batteries which can be loaded from outside, as well as the complete your IC engine technology, and that would remain at least for 10-15 years. The plug-in hybrid technology, uh, before the electric vehicle will start coming in the picture, and that obviously that will be totally IC engine free in that direction. But believe me, nowadays people are thinking to put a small scale IC engine still in the electric vehicle as a called as range extender, so that in case something happens that my battery discharges and there is no possibility to charge it, then the range extender can basically with a small two size cylinder can take me to the next next charging station. So it is becoming more or less a standard in the Scandinavian countries to have a range extender thing on it. So that also will play a very important role. And yeah, so no doubt IC engine era is decreasing or it is going away, but still at least 20 years you will see that IC engine is still existing, and IC engine will still remain as the third part of e-mobility using the synthetic fuel. So synthetic fuel is a, I would say it's coming up in big way. At present, synthetic fuel is basically very expensive. And what is synthetic fuel for the students? It is basically you are taking carbon dioxide from the atmosphere and using that basically carbon dioxide, and then using so oxygen and at the same time hydrogen from the electrolysis process using the renewable energy, you make the synthetic diesel or synthetic petrol or synthetic methane, and that is basically is a CO2 free, because you are not adding any new CO2 to the atmosphere, and that is going to be the next trend also, which will also will be called as a zero CO2 free mobility. No problem.
Yes, yes. There are a few questions,
Yes,
sir.
yes.
Can you
Please go
So
on.
the question from Dr. Anup Chauhan sir is, sir, what are the patterns of innovations in battery technology? Is it material and simulation driven only? What are the other
Uh,
possible research
yes.
uh,
So
directions
basically,
apart from
right.
recycling of lithium ion batteries?
Yeah, recycling is coming up in big way. You will see around say 20% patterns in the recycling area. 30% patterns, if you see the worldwide, obviously dominated a lot from China and Korea. It is in the manufacturing processes, manufacturing of basically how you can manufacture the lithium ion technology differently. Uh, then the chemistry plays a role, and from that, the 10% of the patterns are mainly on the electrolyte because electrolytes play a very important role. And how which additives can give you more electrolytes, better electrolyte additives, that is something more chemistry oriented, but coming up in big way. And basically lot of patterns are coming in the direction of solid state batteries. Solid state batteries, how to manufacture those things, what how we can make it solid state batteries more effectively. But overall, you can say that more than 30% pattern, that is a big chunk of patterns, are mainly in the process of manufacturing of batteries. The processes plays a more important role, and there we our mechanical engineers and manufacturing engineers can play a very important role.
Okay.
Yeah.
Yeah. So one more question by Shreyas Nagvekar. Which battery is better, lithium or sodium ion battery?
Yeah, this is a very interesting question. Basically, lithium, as I told you, has a wonderful advantages, and the four advantages: one is in solid state available, high boiling melting point 180 degrees centigrade, low weight, because of the third in the periodic table. And the fourth, which I have not told you, it has a very good property to build good SEI, solid electrolyte interface, on the anode side. And because of it, it has also very high energy density and a good cycle life, around 4,000. Now, people have talked a lot about the sodium batteries in recent years, and it was dominated mainly from the CATL, a Chinese company, who said that they are going to give a basically high energy density sodium. But if you see in that paper, you will see that the energy density will be still 20% less than lithium. Secondly, the sodium has a problem that sodium ions are bigger and that will not intercalate inside the graphite. It means you will need a basically hard carbon or some other kind of basically matrix to hold that sodium. And we know that the graphite has a very good basically structural properties because it has a very good layers where the lithium ion can go inside it and intercalate. If you go for hard carbon, it does not have that random structure. It has a basically it has a very random structures. It does not have that good properties. So we have to compromise on that. And the very important thing is that sodium up till now has not been able to produce the good SEI. The SEI produced by sodium on the anode side was weak and it was breaking away. So these four questions are always basically in everyone's mind, and practically no paper in from CATL is able to answer those things. And I have also not seen a really working sodium ion batteries with the same properties of lithium ion batteries. So I have still doubts with the sodium ion batteries. Unless no one can answer me how we are building up that good SEI with the sodium, I would not take that case very seriously, frankly speaking. But yes, there are a lot of literature coming up, but more on the marketing side than on the more on the say technical side of it. I hope that it comes up, that we find a viable solution with sodium, because at least it will relieve the pressure from the lithium, because we have limited lithium available in the earth.
Okay, sir. So one more question. What
Yes.
about use of lanthanide or actinide metals in batteries?
Basically, these active materials are basically, yeah, one can use it. Lanthanum is basically used mainly in the terms of electrolyte for the solid state battery. Lanthanum is a ceramic base. Otherwise, I have not yes seen much application in that, especially uh, I would not give a wrong answer to that, but frankly speaking, I have not come across much of these batteries, because our main focus is on lithium ion batteries.
Okay, sir. Sir, one question from my side. As you said, there's an talked about range
Yes,
extender in EV batteries. So, is it available now at present, and how long it gives the batteries? Like, what is the time it will be
yes.
providing us the energy there?
Has a two-cylinder engine. but because of that downsizing of your engine and everything, the range extender is basically available in BMW i3 and other places also, where actually you can see that you have basically combination of both of them is there available. I think
Mhm.
BMW only has come with a range extender. The other companies
Okay.
are thinking of whether to have a range extender or only to have a range extender
So
or
what
only
is
to
like
continue
what are the
to have a
negatives
range extender.
about of the range
Yes, and
extender?
because
What are the
normally it depends on the tank. The tank size is normally around 10 liter or something
okay.
tank size is there. Yeah. So basically we are talking
Mhm.
about 10-liter size of tank, not more than that, and two-cylinder engine. So that is basically the whole concept is like, a smaller, basically
Mhm.
a smaller tank size of 10 liter, which would give maximum
Hello. Hello. One more question, sir. Yeah. Hello, sir. Am I audible? Yes, yes. One more question, sir, from Dr. Zakir Ilai, sir. What about comparative environmental hazardous effects due to extensive use of these batteries? Sir, Karthik, sir, I guess he's lost the range or some problem with this internet. Anyways, very nice session is going on, and the questions are coming. Maybe. Yeah, some internet issues, maybe, sir. We are still here, sir. The session is going very nice. Question answer session. Good questions are coming up. I request other students and faculty members also to put on their questions. He'll rejoin, I guess. Sir will rejoin the meet to answer our questions. I hope our students must have gained a lot of knowledge about these batteries. Yeah, sir has come. Yeah. Hello, sir. Karthik, sir.
Hello.
Yeah. Hello, sir.
Yeah, I can hear
Sir,
you.
there
I
was
can
one
hear you.
question. Yes, sir.
I'm just opening that file for the range.
Yeah, yeah. Fine.
Yeah, I can
Sir, your voice is actually
just
not, yeah, some internet issues, maybe, sir, from your side. Karthik, sir. Yeah. Karthik, sir, are you there? Yeah, yeah, yeah. So we'll wait for him for some more time. Maybe the problem may be resolved. Yeah,
Can you hear me?
Karthik, sir. Yeah, yeah. We can hear you,
Yeah,
sir,
yeah.
now.
I'm just showing one slide where you can see the range
Okay.
extender. Okay.
Yeah, sir.
I'm just showing that slide. So basically, this is about the range extender. This is BMW i3. And if you can see that
Mhm.
basically my lithium ion is very small batteries, around 18.8 kilowatt hour, that will give you around, say, 100, uh, around 150 kilometer range. And the driving range
Okay.
is basically NEDC, and the range extender gasoline tank capacity is only 10 liter. And your basically 25 kilowatt of that engine is available with that. So this is basically the range extender which is available. And yeah, so this is basically the small downsize engine. That is the
Okay.
main idea behind it.
So one more question was raised by Dr. Zakir Ilai, sir.
Yeah.
What about comparative environmental hazardous effects due to extensive use of these batteries?
Actually speaking, the only hazardous material which is available here is the cobalt and nickel. Nickel being, we know that is allergic. The cobalt is basically carcinogenic. And the rest of the material, if you see, are not having a problem. Yes, the electrolyte can release some gases, which is the hydrofluoric acid, which are normally strong acid base, but that is basically done inside the cell. It is not coming out. And the material which is used to produce the slurry on the cathode side, it is basically NMP, Na-methyl pyrrolidine. This is basically uh, not basically, it is again recycled and used again and again. So frankly speaking, we have not much hazardous particle which is left inside the battery, as if especially only for the cobalt part of it.
Very nice. So we can reuse those batteries. Very
Right,
nice.
right. And NMP, we cannot remove it outside. We have to recycle it again and again. So most of the parts which is hazardous will be recycled by the same company and will not be thrown out.
Okay. So one more question. Can I, sir?
Yes, yes, please go on.
A vehicle and IC engine have less carbon footprint or EV as in EV? In EV, that is. The battery which is manufactured are also leaving carbon footprint. When we manufacture them, so overall, which vehicle have less carbon footprint?
So basically, your normal IC engine has a less carbon footprint, no doubt about it, because your energy need to produce the car, electric vehicle car, and especially the batteries is a very high energy intensive process. So if you would say that your car, if you just compare the car, manufacturing it, then no doubt your IC engine is going to be better CO2 footprint. But if we consider the operation, like complete life cycle analysis of that, then what we'll realize that no doubt your carbon footprint is basically higher in making EV car, but during the operation time, it is basically zero CO2. And that is finally giving us better advantages. So if you see the life cycle analysis, we would see that we would at least still need around 100,000 kilometers to run with electric vehicle to run to that break-even point of zero CO2. After that, only that's like we can get the advantage of zero CO2 with electric vehicle car. Before that, the IC engine will have a benefit of it. Or obviously, nowadays people are also thinking of making the complete car manufacturing also with renewable energy. In that case, basically, you can say that that whole break-even point will reduce more drastically. So all battery manufacturing companies, car manufacturing companies are forced to go for the renewable energies and zero CO2 energies for the factory production also. That would automatically help them. But at present, it has still not happened. And the batteries are using raw materials like graphite, synthetic graphite, which is highly CO2 intensive manufacturing process because it's mainly coming from China. But believe me, this will also change in a lot of places where they will be also forced to use renewable energies.
Okay.
The last question, please. Sorry. So should I answer that again? Yeah,
There
yes,
are few
please go on.
questions.
Please go on.
Ibrahim sir, will you please read out the question for him?
Yeah, basically the gassing would happen all the time because what happens that electrolyte is coming in contact with the cathode, and the cathode is basically having high voltage of around 4.2 volt. So at that particular voltage, some kind of gassing will be produced and that cannot be removed. But your cell can withstand that much of say around 6 to 8 bar of internal pressure, and the gas will remain inside it. But yes, if there is some gases which are coming because of the normal procedure, then this gas would be like a carbon dioxide gas and the methane gas and some kind of hydrofluoric acid gas, which would be basically judged by our. We put lot of gas sensors also inside our battery pack, and if those normal gases are there, they would basically go out in a small amount in the atmosphere, but it is a very small amount. especially CO2 and methane is not a dangerous. It's a very small amount, and hydrofluoric acid could be a small amount which will go away. Only when there is a thermal runaway, at that time the gases produced are very high in the fast way, and there the main gas produced are basically the carbon monoxide and the hydrogen. These are two main gases which are produced, and that gases will be easily identified by sensors, and that will also basically start your safety mechanism, like your pyrofuse will be closed, your BMS will react very fast to this situation and try to prevent the thermal runaway. So we know which gases are produced during thermal runaway and which gases are produced during normal operation. So normal operation gases are coming in slow amount most of the time, but it will remain in the cell most of the time, because cells are really packed, so densely packed that it does not happen. Even if it is pouch cell, it can hold 8 bar of pressure, and normally the gases during the lifetime of the cell does not blow away. So does not blow these cells away. The sealing is quite good enough, and this is all tested. This is tested by the manufacturer. Normally there is a testing called calendric aging or high temperature aging. The cells are put at 100% SOC at 70 degrees centigrade. I'm talking about 70 degrees centigrade for 180 days to check it if there is no venting happening or not, or there is no gas evolution happening. And only if that condition passes, then only the cells can go into the market. So there are a lot of tests which has to go into this test, into the cells. And that's why I would say that normally the gases which is happening during the normal operation of the cell would not come out of the cell area. So don't worry about it. And plus your battery module is also helium tight sealed, and the battery system is also helium tight sealed. So there are also no chances that the cell gases can come out. Only it can come out is during the thermal runaway. But after that, during thermal runaway, anyway, you will be out of the car. So should not be a problem for you.
Okay. Thank you. Okay, sir. Sir, shall I conclude ask Katya ma'am to conclude the program?
Yes, from my side, fine.
Yeah. Now I request Professor Atya ma'am to conclude our program with vote of thanks. Atya ma'am.
Hello.
Yes.
Am I audible?
Yes, you are audible.
Hello.
Yes, Atya ma'am, you are audible.
Yeah. Thank you very much, ma'am. First of all, thank you very much, NDLI Club, for giving me this opportunity to give vote of thanks. We are very much thankful for our management, our respected director sir, principal sir, vice principal sir, for giving permission to organize this event. A big thank you to Dr. Kartik Jamadar sir, who has given this session. It's fantastic. Though I am from civil branch, but I have understood and I have learned so many things about batteries. Thank you very much, sir. And last, not the least, the main organizing committee, as NDLI Club has organized this event in association with Mechanical and Automobile Engineering Department. So the faculties who are directly and indirectly involved in the organizing this event, I'm very much thankful to them. Okay, and thank you all the audience. Thank you very much.
Thank you. It was a pleasure too. Yeah.
Thank you.
Even we had nice time with you, sir. Thank you, sir.
Thank you. Bye.
Bye. I request all the participants to leave the meeting.
Okay.
Ibrahim, sir, I think yeah, he's there.
Yes, sir. Yes.
Even I would like to thank Dr. Zakir Lai sir and Farheen ma'am to start the program very effectively. Very nice. Yeah.
Sure, sir. Sure.
I will visit IV.
IV. He's on IV, I guess. On Monday.
Monday I will be on
Shahab Dabi. Shahab Dabi, sir, he will be on industrial visit. Okay, fine, sir. So we'll leave the meeting. Fine.
Thank you. Thank you.
Thank you, yes, sir. There are some students, I guess, who are still in the line. So we'll end off the meeting, Ibrahim, sir. I think so. He has ended up with the meeting. Yes. Okay, sir. Fine. Yeah. Goodbye. Yeah. Thank you.
Bye, sir.